Space is not the silent void we imagine it to be. This journey will reveal 30 of the strangest and most wonderful truths hidden in the history of space exploration. You will discover stories of cosmic oddities, breathtaking human ingenuity, and science so mind-bending it will permanently alter how you see our universe. We will uncover why astronauts come home taller, what the vacuum of space supposedly smells like, and how a single, mysterious radio signal from the depths of the galaxy has defied explanation for decades. By the end, the familiar night sky will feel entirely new. What do you believe is waiting for us out there? Our journey begins not with a triumph, but with a quiet sacrifice. The first living being to orbit our planet was a small, gentle stray dog plucked from the streets of Moscow. Her name was Laika. In November of 1957, the Soviet Union stunned the world by launching Sputnik 2, a spacecraft carrying this unassuming passenger. The mission was a desperate, politically charged dash for glory, a direct response to the shock of the first Sputnik success. Scientists needed to know if a living creature could simply survive the violent forces of launch and the unknown environment of weightlessness. Laika was fitted with sensors to monitor her heartbeat, her breathing, her movements. She was a pioneer in the truest sense, venturing into a realm no Earth-born creature had ever seen. But from the very start, her story was shadowed by a heartbreaking truth. The technology for a safe return did not yet exist. There was no re-entry plan. Everyone involved knew Laika was on a one-way journey. For decades, the official story was that she lived for several days in orbit, her vital signs beaming back precious data, before she was humanely euthanized with a planned dose of poisoned food. It was only in 2002 that a key scientist revealed the grimmer reality, that Laika likely died from panic and overheating within just a few hours of reaching orbit. Her short life and lonely death ignited one of the first major ethical debates of the space age. Was this sacrifice justified by the scientific leap it enabled? Could we, as a species, justify sending a helpless creature to die for our ambition? Laika's legacy is profoundly complex, a bittersweet mix of cold political calculation and genuine scientific curiosity. She is both a celebrated pioneer whose courage paved the way for human spaceflight and a poignant symbol of the costs buried within our greatest achievements. Her memory reminds us that every giant leap for mankind often begins with a single, small, and sometimes tragic step. Laika's story shows how space changes a living body in profound and permanent ways, but some of those changes are surprisingly reversible. Consider this: an astronaut can leave Earth and return noticeably taller, having gained up to 2 inches in height during their mission. This is not science fiction. It is a well-documented physiological quirk of life in microgravity. The secret lies in your spine. On Earth, gravity constantly compresses the stack of soft, gel-filled cushions between your vertebrae, known as spinal discs. They are like tiny, fluid-filled pillows that absorb shock and allow for flexibility. In the weightlessness of space, that constant downward pressure vanishes. Freed from gravity's grip, these discs expand, like sponges slowly soaking up water and puffing out. The entire spinal column gently stretches, and the astronaut gains a little extra height. For a short time, they are literally a taller version of themselves, but this cosmic growth spurt is entirely temporary. Once back under the influence of Earth's gravity, the process reverses over a period of weeks. The discs compress again, and the astronaut returns to their original height. This expansion and contraction is not without consequence. That stretching can irritate the nerves and muscles along the spine, and the recompression upon return is often the source of significant back pain and stiffness for many astronauts. It is a direct physical reminder that our bodies are perfectly adapted for a world with a constant downward pull. When that pull disappears, even our skeleton responds in unexpected ways. This temporary change highlights a beautiful and strange truth that we are not rigid beings but adaptable ones, shaped in every detail by the world we call home. Our spines are not the only part of us that can find a new home beyond Earth. The moon, that silent companion in our sky, holds a far more permanent human connection. It is home to a celestial cemetery. Scattered across its dusty plains are the ashes of a select few who dreamed of touching that world. The most famous of these is Eugene Shoemaker, a man who dedicated his life to studying planets and impacts but was barred from becoming an astronaut due to a medical condition. His greatest passion was the moon, and he trained the Apollo astronauts in geology, teaching them how to read the lunar landscape. When he died in a car accident in 1997, his wish was to finally go to the moon. 2 years later, NASA Lunar Prospector mission carried a small capsule containing an ounce of his cremated remains. The spacecraft was deliberately crashed into a crater at the moon's south pole, a final poetic act. Shoemaker's ashes now rest forever in the very type of geological feature he spent his life studying, a permanent part of the landscape he loved. He is, to this day, the only human whose remains lie on another world. But his is not the only attempt at a lunar burial. In 2019, a private company's spacecraft carrying a small library of human knowledge and capsules of cremated remains from paying customers attempted a soft landing. It failed, crashing onto the surface. This blend of solemn remembrance and commercial ambition creates a strange new chapter in our relationship with space. It raises profound questions. Is the moon a sacred place, a scientific preserve, or a frontier open to all forms of human legacy? Sending our remains into the cosmos is the ultimate act of reaching for the stars, a desire to become part of the universe itself, long after our time on Earth has ended. That desire to become part of the cosmos is a profound one, yet space itself leaves its own distinct mark on those who visit. When astronauts return from a spacewalk and finally remove their helmets inside the airlock, they are often greeted by a powerful, unexpected smell clinging to their suits. It is a scent described in surprisingly consistent terms, a strange metallic aroma like seared steak, hot metal, or the sharp fumes from a welding torch. This is not the smell of the spaceship's interior, it is the smell of space itself, carried in on the fabric and tools that were exposed to the pure vacuum. The vacuum of space, of course, has no air to carry scent molecules to your nose, but when the airlock repressurizes, those compounds that have settled on the suit's surface are released into the cabin's atmosphere, creating this bizarre sensory report. So what is creating this universal metallic perfume? The leading theory points to the violent, energetic deaths of stars. In their final moments, massive stars churn out complex molecules called polycyclic aromatic hydrocarbons. These are sturdy, carbon-based compounds that can survive the harsh journey through the interstellar medium. They drift for eons, eventually becoming part of the molecular clouds where new stars and planets are born. Astronauts floating outside their spacecraft are essentially dusting themselves with the faint residue of ancient stellar explosions. The high-energy vibrations of these molecules, activated by unfiltered solar radiation, are what our noses interpret as that sharp, burnt metal scent. It is a haunting thought that the smell clinging to a spacesuit is the ghostly aroma of a star that died millions of years ago, a sensory connection to the grand and violent cycles of the universe, all wrapped up in a scent we instinctively recognize from a backyard barbecue or a machine shop. That ghostly scent of dead stars is a whisper from the void, but for decades, Mars seemed to scream back with a more menacing message: stay away. In the 1960s and 70s, as engineers at NASA, a jet propulsion laboratory, struggled to reach the red planet, a darkly humorous superstition was born among them. They called it the Great Galactic Ghoul. This was a mythical, ravenous space monster that supposedly lurked in the void between Earth and Mars, lying in wait to devour any spacecraft foolish enough to attempt the journey. It was a joke, of course, a way for brilliant minds to cope with a string of heartbreaking, expensive failures that defied easy explanation. The evidence for the ghoul's appetite seemed overwhelming. Consider Mariner 3, America's first attempt at a Mars flyby in 1964. Its protective shroud failed to jettison after launch, leaving the probe trapped inside a metal cocoon, its solar panels unable to deploy. It was a silent, dead weight tumbling toward the sun, a mission lost before it even began. The Soviet Union fared no better. Their early Mars program was a litany of catastrophes, from rockets that exploded on the launch pad, to probes that fell silent just after leaving Earth, to the infamous Mars 2 lander in 1971, which became the first human-made object to reach the Martian surface, only by crashing into it at high speed. Mission after mission would vanish, go silent, or fail at the last possible moment. The pattern felt uncanny, almost personal. The great galactic ghoul became the personification of all the unknown variables, the brutal mathematics of orbital mechanics, the sheer bad luck that made Mars a graveyard for robotic explorers. It was easier to blame a monster than to accept that space is simply, inherently, unforgivingly hard. But myths are made to be broken by perseverance. The turning point came with the stunning success of Mariner 9 in 1971. It not only survived the ghoul's domain, it became the first spacecraft to orbit another planet, arriving at a Mars shrouded in a global dust storm. Patiently, it waited for the skies to clear, and then it revolutionized our understanding, revealing a world of giant volcanoes, vast canyons, and ancient riverbeds. The ghoul had been defeated not by a hero, but by better engineering, relentless problem-solving, and hard-won experience. The story of the great galactic ghoul is not one of a real monster, but of the very human need to find patterns in chaos, and the even more human triumph of finally, painstakingly, deciphering that chaos into knowledge. The defeat of the great galactic ghoul proved we could reach other worlds, but it left a deeper question hanging in the void. What would we say if we were heard? In 1977, as the twin Voyager probes began their grand tour of the outer planets, they carried with them humanity's most ambitious attempt at an answer, a pair of golden phonograph records. These were not scientific instruments, but time capsules intended to survive for 1 billion years and drift among the stars long after our civilization, and perhaps our very planet, are gone. Their contents were chosen by a committee led by the visionary astronomer Carl Sagan, a task of unimaginable pressure to represent all of Earth in 90 minutes of sound and 116 encoded images. Imagine the challenge, compressing the entirety of the human experience onto a single disc. The team curated a symphony of our planet, a collection of natural sounds that tell the story of a living world. They included the roar of volcanoes, the crash of ocean waves, the patter of rain, the songs of birds and whales, and even the heartbeat of a human being and the laughter of a child. Then came our own creations, a musical journey spanning cultures and centuries, from the soaring complexities of Bach and Beethoven to the driving rock and roll of Chuck Berry's Johnny B. Good, from traditional folk songs of Bulgaria and Senegal to the ancient court music of Japan. The visual images, painstakingly encoded in analog form, showed everything from mathematical diagrams and DNA structures to photographs of a nursing mother, a bustling supermarket, and the Great Wall of China. But perhaps the most poignant element is the collection of spoken greetings, 55 languages from ancient Akkadian to modern Welsh, each offering a simple hello from our world. Among them is the voice of then United Nations Secretary-General Kurt Waldheim, speaking on behalf of a divided but hopeful species. His message simple: we step out of our solar system into the universe seeking only peace and friendship, to teach if we are called upon, to be taught if we are fortunate. The Golden Record is not a scientific document, it is a bottle cast into the cosmic ocean, a hopeful shout into an unimaginably vast silence. It carries no threats, no maps, just a humble sampler of who we were and who we hoped to be in the late 20th century. It is our most profound and optimistic message to the future, a whisper saying we were here. That hopeful message in a bottle requires immense resources to send, and every single drop of water on board a spacecraft is more precious than gold. To survive for months in the void, astronauts must become masters of a closed-loop system, a reality that leads to one of spaceflight's most misunderstood necessities. They drink water that was once their own urine. The instinctive reaction is a firm no thank you, a yuck factor deeply wired into our biology. But on the International Space Station, this process is not just acceptable, it is an absolute marvel of engineering and a non-negotiable requirement for survival. Think about the numbers. Launching anything from Earth costs thousands of dollars per pound. Transporting enough water for a crew of 6 for a year would require thousands of heavy, bulky containers, a logistical and financial impossibility. The solution is elegant and brilliant: recycle everything. The station's water recovery system is a complex network of filters, processors, and chemical treatments that mimics and accelerates Earth's own natural water cycle. It collects every possible source of moisture, from cabin condensation and shower runoff to, yes, astronaut urine and sweat. The urine undergoes a rigorous multi-stage purification. First, it is distilled in a vacuum chamber where the low pressure causes the water to boil at room temperature, separating it from the solid waste. That distilled water then joins all the other collected wastewater and goes through a series of sophisticated filters and a catalytic reactor that breaks down any remaining trace contaminants. Finally, iodine is added to prevent microbial growth, just as we use chlorine in water on Earth. The result is water that is chemically purer than what most of us drink from the tap. The system is astoundingly efficient, recovering over 90% of all water on the station. This turns a daily human function into a critical part of the life support chain. An astronaut's coffee this morning was quite literally their colleague's coffee from yesterday. This technology transforms a weird fact into a profound wonder. It is the key to unlocking the solar system. For a future moon base or a 2-year voyage to Mars, there are no resupply missions. The spacecraft must be a self-sustaining ark. The ability to perfectly recycle water and air is what makes such dreams physically possible. It reframes our relationship with our own bodies and our resources, seeing waste not as an end product but as the vital starting material for tomorrow's survival. The golden record is our hopeful message to the cosmos, but what if a message came back? On a warm August night in 1977, a quiet revolution was taking place at Ohio State University's Big Ear radio telescope. As the massive dish scanned the sky, its computer printed out long reams of paper, rows and rows of letters and numbers representing the faint radio whispers of the universe. For astronomer Jerry Amon, it was another routine shift, volunteering to sift through this cosmic static. Then his eyes caught something extraordinary. On the printout from August 15th, a sequence of characters stood out with shocking intensity. The signal was so strong, the telescope's system used the letter code 6EQUJ5 to represent its peak. Amon, stunned, grabbed a red pen, circled the alphanumeric string, and in the margin he wrote a single, powerful word. Wow, that 72-second burst of radio noise has never been repeated, and its origin remains one of the most tantalizing mysteries in the history of astronomy. What made the WOW signal so special? First, its frequency. It was detected at 1420 MHz, a protected band of the radio spectrum where earthly transmitters are forbidden to broadcast, a quiet channel reserved for listening to the universe itself. Second, its shape. As the Big Ear's fixed dish scanned due to Earth's rotation, the signal rose to a brilliant peak and then faded away exactly as you would expect from a distant, pinpoint source passing through the telescope's beam. All the evidence pointed to a signal originating far beyond our solar system, possibly even beyond our galaxy. The hunt was on. For decades, astronomers have pointed radio telescopes back at that same spot in the constellation Sagittarius, listening intently for a repeat performance. Silence, the signal never returned. The theories, however, have multiplied. Could it have been a natural cosmic event, like the flare of a distant star or the echo of a comet? Some scientists proposed it was hydrogen gas from two passing comets, but the timing and the comet's positions did not quite match up. Others suggest it was a one-time event, like a massive asteroid collision in a far-off star system, or a burst of energy from an exotic type of star we do not yet understand. Then, of course, there is the possibility that lingers in the back of every scientist's mind, the one Jerry Amon himself considered, that it was a transient signal from an intelligent civilization. The WOW signal endures because it is a perfect cosmic riddle, a single, brilliant flash of what if etched onto a piece of now yellowing paper. It is a reminder that the universe is vast enough to hide profound secrets in plain sight, offering a glimpse of something wondrous and then retreating back into the silence, leaving us forever to wonder what or who said hello. The silence of space is now crowded with ghosts. Orbiting our planet at thousands of miles per hour is a growing cloud of human-made debris, a celestial graveyard of our own ambition. This is not a metaphor, it is a physical reality, a shell of forgotten technology that now threatens our future in space. Picture a defunct satellite the size of a school bus, tumbling end over end in perpetual freefall. Now imagine a tiny fleck of paint from a rocket's exterior, no bigger than a grain of sand, at orbital velocities which can exceed 17,000 miles per hour. That tiny paint chip carries the kinetic energy of a bowling ball thrown at full force. It can crack a space shuttle window, puncture a fuel tank, or disable a critical satellite. And there are over 100 million pieces of this debris currently tracked, from dead satellites and spent rocket boosters to lost tools, frozen coolant droplets, and the shattered fragments of past collisions. This is the orbital junkyard, and it is growing more dangerous every year. The greatest fear is not a single impact, but a chain reaction known as the Kessler syndrome. Proposed by NASA scientist Donald Kessler in the 1970s, this theory paints a chilling scenario. One major collision in a crowded orbital lane, like the 2009 crash between a defunct Russian satellite and an active American one, creates thousands of new fragments. Each of those pieces becomes a new high-speed projectile, dramatically increasing the probability of further collisions. Those collisions create more debris, which leads to more crashes, triggering an unstoppable cascade. In a worst-case scenario, certain orbits could become so saturated with shrapnel that they are rendered unusable for centuries, a permanent barrier of swirling metal that traps us on Earth. The International Space Station is not a passive observer to this threat, it is a constant target. Several times a year, the station must fire its thrusters to perform a debris avoidance maneuver, nudging itself out of the path of a tracked object. The crew also regularly retreats into their soy as lifeboats when a piece of debris is detected too late to move, ready to evacuate if a strike compromises the station's hull. But this is not a hopeless problem. The same ingenuity that created this mess is now working on the cosmic cleanup. Engineers around the world are developing what are essentially space garbage trucks. The European Space Agency is planning a mission called Clear Space One, which will use a robotic arm with 4 articulated legs to capture a large piece of debris and safely guide it to burn up in the atmosphere. Other concepts are even more inventive, testing giant nets that can ensnare tumbling objects or harpoons that can spear them and reel them in. There are even proposals for ground-based lasers that could nudge smaller pieces into safer orbits by gently pushing them with photons. These solutions are in their infancy, and the political and financial challenges are immense, but they represent a crucial shift in thinking. We are moving from simply launching things into space to taking responsibility for the environment we have created there. The orbital graveyard is a stark monument to our carelessness, but the emerging field of active debris removal is a testament to our capacity for course correction, a necessary step to ensure the pathways to the stars remain open for generations to come. Clearing the orbital graveyard is a fight for our future, but it requires us to first remember our profound place in the cosmos. In February of 1990, from a staggering distance of 3.7 billion miles, the Voyager 1 spacecraft turned its cameras back toward a home it would never see again. At the request of the astronomer Carl Sagan, the probe took a series of final photographs of our solar system. In one of these images, a single, pale blue pixel is suspended in a vast, sunlit darkness. That pixel is Earth. The photograph, famously titled Pale Blue Dot, captures our entire world, every human who has ever lived, every triumph and tragedy, every forest and ocean, not as a globe, but as a mote of dust adrift in an unimaginable void. Taking this portrait was a monumental technical challenge. Voyager was so far away that the sun was still blindingly bright, risking damage to the camera's sensitive optics. Engineers had to use the narrowest of filters and the shortest possible exposure to capture the dim, distant planets without burning out the image. Earth, in this cosmic family portrait, was almost lost entirely, a tiny speck caught in a stray sunbeam, a cosmic afterthought. But it was this very insignificance that gave the image its staggering power. Carl Sagan's reflection on the photograph remains one of the most poignant pieces of writing in scientific history. He wrote, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. The pale blue dot offers no borders, no divisions, no markers of power or wealth. It reduces the human saga to its most fundamental truth. We are alone together on a fragile, precious speck, utterly isolated in the cosmic dark. This perspective is not meant to diminish us but to unify us. It frames all our conflicts, all our ambitions within a context of breathtaking humility. The photograph is a silent argument for stewardship, for compassion, for recognizing that in the face of the infinite, our only true homeland is that one pale blue dot. It is a reminder that every mission we send into the void, every piece of debris we must now clean up, every wonder we discover, begins and ends with the care of that single, vulnerable pixel in the endless night. That pale blue dot is a world of profound emotions, but expressing them in space requires a whole new rulebook. In the weightlessness of orbit, even a simple human cry becomes a strange and challenging physics experiment. Without the constant pull of gravity, tears do not roll down your cheeks. There is no downward path for them to follow. Instead, they simply well up in the eye, clinging to the surface tension of the eyeball itself. The liquid gathers into a growing, quivering dome that blurs your vision. If you let it continue, that dome can become a large, wobbling bubble of saline clinging stubbornly to your face. Eventually, with enough accumulation or a slight shake of the head, the entire bubble can detach and float away as a perfect, shimmering sphere of sadness drifting through the cabin. While this might sound almost poetic, astronauts report it is far from pleasant. That large bubble of fluid can cause a stinging sensation, as the salt and proteins in the tears have nowhere to drain, irritating the eye far more than a normal cry on Earth. It can also create a disorienting, watery lens that makes it difficult to see your work. So how do you handle a moment of grief, frustration, or overwhelming beauty when you cannot properly cry? Astronauts learn to be proactive. At the first sign of tears, they will quickly grab a towel or a specially designed absorbent cloth and gently dab the fluid away before it can form that large, uncomfortable bubble. They manage their emotions with a practical, almost clinical efficiency that the environment demands. This tiny, quirky fact reveals a deeper truth about life off the planet. In space, the most intimate, involuntary human behaviors are rewritten by an alien physics. The body's instinctive responses no longer function as designed. A sob does not lead to cathartic tears rolling away. It leads to a floating, stinging nuisance that must be dealt with. It is a constant, low-level negotiation between being human and being an astronaut, where even your tears must be consciously managed. This is the reality of living in a world that was never meant for us, where every drop of water, even the ones born of emotion, must be accounted for and controlled. That fragile blue dot is protected by an invisible shield, one that creates a perilous gauntlet around our planet. Encircling Earth are two vast, donut-shaped rings of pure energy known as the Van Allen radiation belts. Imagine a pair of colossal, shimmering halos, one nested inside the other, stretching from about 400 to 36,000 miles above the surface. They are not solid but seething oceans of high-speed protons and electrons, trapped and whipped into a frenzy by our planet's powerful magnetic field. This discovery was one of the first great surprises of the space age. In 1958, America's first satellite, Explorer 1, carried a simple Geiger counter built by scientist James Van Allen. As the satellite soared higher, the instrument's readings went off the charts before suddenly dropping to zero. At first, the team thought the sensor had failed. The brilliant realization was that it hadn't failed, it had been overwhelmed. The radiation was so intense it saturated the counter, making it appear dead. Earth was not floating in an empty void, but was cocooned within a torrent of deadly particles. This revelation sent shockwaves through the nascent space program, for these belts posed a clear and present danger. For an astronaut, passing through the heart of the most intense regions would be like spending hours inside a nuclear reactor, receiving a lethal dose of radiation in minutes. It was a seemingly impassable barrier on the road to the moon. When President Kennedy committed America to a lunar landing, engineers faced a terrifying puzzle. How do you send fragile humans through a zone of certain death? The answer was a masterpiece of precision and cleverness, not brute force. They realized the belts were not a uniform wall of radiation. The most hazardous areas are concentrated in specific zones. By plotting a trajectory that skimmed quickly through the thinner, outer edges of the belts, the Apollo spacecraft could minimize exposure. The entire transit through the most dangerous regions took only about an hour, and the spacecraft's aluminum hull provided just enough shielding to keep the dose within survivable limits. The astronauts themselves reported seeing strange flashes of light with their eyes closed, caused by cosmic rays zipping through their retinas, a silent reminder of the energetic storm they were navigating. The myth that the Van Allen belts made the moon landings impossible is a profound misunderstanding of the ingenuity involved. NASA did not blast through them, they danced around them. This was not about having a shield strong enough to stop the radiation, but about having the knowledge and the navigational skill to take the safest possible path. The belts were not a stop sign, they were a treacherous mountain pass on the cosmic map, and learning to cross them was one of humanity's first great lessons in surviving the harsh realities of interplanetary space. Our planet's silent companion is not as permanent as it seems. The moon is in a slow, steady retreat, drifting away from Earth at a rate of about 1.5 inches every single year. You could not perceive this movement in a human lifetime, but over the eons, it adds up to a profound reshaping of our celestial relationship. The force behind this cosmic drift is the same one that creates the ocean's tides. As Earth rotates, the gravitational pull of the Moon drags a tidal bulge of water across our planet's surface. But Earth spins faster than the Moon orbits, so this watery bulge is actually pulled slightly ahead of the point directly under the Moon. That forward-leaning mass of water exerts its own tiny gravitational tug on the Moon, pulling it forward in its orbit, like a parent giving a gentle push to a child on a swing. This constant nudge transfers a little bit of Earth's rotational energy to the Moon, pushing it into a slightly higher, slower orbit. In exchange, Earth's own spin is ever so slightly braked, lengthening our day by about 1.7 milliseconds per century. The implications of this gentle dance stretch into an almost unimaginable future. Billions of years from now, the Moon will be significantly farther away. Our days will be longer, perhaps stretching to over 30 hours, and the most breathtaking celestial event we know, a total solar eclipse, will become a relic of the past. The Moon will appear smaller in the sky, and its disk will no longer perfectly cover the Sun. Instead of the awe-inspiring totality we experience today, future observers will see only annular eclipses where a brilliant ring of sunlight, a ring of fire, surrounds the dark silhouette of the Moon. It is a humbling thought that the cosmic clockwork we take for granted is not a fixed setting, but a snapshot in a slow-motion ballet. The stability of our sky is an illusion of brevity, a temporary harmony in an ever-changing solar system. The Moon's slow retreat teaches us that our cosmic perspective is always shifting, and sometimes our eyes can play the most profound tricks on us. In July of 1976, a spacecraft orbiting Mars captured an image that would ignite a global firestorm of imagination. The Viking 1 orbiter was systematically mapping the Martian surface in the Cydonia region when it photographed a geological formation roughly a mile across. The Sun was low in the sky, casting long, dramatic shadows across a particular mesa. To the scientists analyzing the data, it was an interesting example of Martian erosion. But when the image was released to the public, one feature leaped out with shocking clarity. The shadows and light, viewed from that specific angle and resolution, formed the unmistakable likeness of a giant, stoic human face staring up from the rusty plains. The face on Mars was born. Newspapers ran sensational headlines, books were written, and a powerful narrative took hold. Here was evidence, proponents argued, of an ancient, intelligent civilization that had once thrived on the red planet, leaving behind a monument to their existence, a Martian sphinx calling out to us across the ages. It was a story that tapped directly into our deepest myths and desires, the hope that we are not alone in the universe and that others have walked this path before us. The frenzy was a perfect case study of a powerful psychological phenomenon called pareidolia. This is our brain's hardwired tendency to perceive familiar patterns, especially faces, in random or ambiguous stimuli. We see the man in the moon, a dragon in the clouds, or the Virgin Mary on a piece of toast. It is an evolutionary survival tool, a way to quickly identify a potential friend or foe in the bushes. In the dusty, unfamiliar landscape of Mars, our pattern-seeking brains latched onto the most familiar shape of all, a human face, and constructed an entire history around it. Science, however, progresses not by embracing the first exciting story, but by gathering better data. As decades passed, new missions arrived at Mars with far more powerful cameras. The Mars Global Surveyor in the late 1990s, and later the Mars Reconnaissance Orbiter, aimed their high-resolution lenses at the Cydonia face. The new images revealed the truth in stunning detail. The face was not an engineered monument at all. It was a completely natural mesa, heavily eroded by millions of years of Martian wind. Its famous features simply the product of chance shadows and a low-resolution camera. The haunting visage dissolved into a rugged, rocky hill, fascinating in its own right, but undeniably geological. This transformation from a wonder to a weathered rock is not a defeat for curiosity, it is a victory for the scientific process. The initial excitement was the spark, the human desire to find meaning. The follow-up investigation, the patient collection of better evidence, was the discipline that refined that meaning into understanding. The story of the face on Mars is a beautiful parable about our relationship with the unknown. It reminds us that our first interpretations are often projections of our own hopes and fears onto a blank cosmic canvas. True discovery lies not in clinging to those first impressions, but in having the courage and the tools to look closer, to let the universe reveal itself on its own terms, even when the truth is less sensational than the myth. It is a lesson in humility, showing that the universe is often stranger and more wonderfully complex than any story we can invent. The myth of a Martian Sphinx reveals how we project our own stories onto the cosmos, but as our ambitions grow, we are learning to write a new kind of story for the stars, one made of laws. Space law is not science fiction. It is a surprisingly established and vital field of international diplomacy, born from the very first beeps of Sputnik. The foundational document is the Outer Space Treaty of 1967, signed at the height of the Cold War by the United States, the Soviet Union, and the United Kingdom. Its core principles were a direct response to the fears of the era, a desperate and hopeful attempt to prevent the nuclear arms race from spilling into the heavens. The treaty declares that space is the province of all mankind, free for exploration and use by all nations. It mandates that celestial bodies like the Moon and Mars be used exclusively for peaceful purposes, explicitly banning the establishment of military bases or the testing of any kind of weapon. Perhaps its most famous and forward-thinking clause is the one that forbids any nation from claiming sovereignty over a celestial body. No country can plant a flag on the Moon and call it its own territory, a rule that has so far kept the final frontier from becoming a scene of colonial land grabs. Furthermore, the treaty establishes that states are internationally responsible for their national activities in space, whether carried out by government agencies or private companies. If a satellite from one country damages a satellite from another, or worse, causes harm on Earth, the launching state is liable. This framework turned space into a global commons governed by a spirit of cooperation and shared responsibility. But the world of 1967 could not have foreseen the challenges of today. The treaty says nothing about private companies mining asteroids for precious metals or billionaire entrepreneurs selling tickets for orbital joyride. This legal gray area is where the new frontier of space law is being forged. Nations like the United States and Luxembourg have already passed laws asserting that companies can own the resources they extract from an asteroid, even though they cannot claim the asteroid itself. It is a legal distinction as fine as a moonbeam, attempting to incentivize investment while staying within the treaty's spirit. Meanwhile, the rise of space tourism forces regulators to answer difficult questions about passenger safety, informed consent for civilians facing the risks of spaceflight, and even the environmental impact of rocket launches on our own atmosphere. Crafting these new rules is a slow, complex dance between innovation and regulation, between the dream of economic expansion and the imperative of preserving space as a peaceful, sustainable environment for all humanity. We are witnessing the first draft of a solar system constitution, a testament to our understanding that the greatest adventures require not just courage and technology, but also a shared agreement on how to behave once we get there. Sometimes the universe speaks in a whisper so faint we almost miss it. For decades, two of our most distant robotic envoys, the Pioneer 10 and Pioneer 11 probes, were telling us something strange. Launched in the early 1970s, these hardy spacecraft completed their grand tours of Jupiter and Saturn, and then kept going, blazing trails toward the edges of our solar system. Back on Earth, a team of scientists led by John Anderson at the Jet Propulsion Laboratory was meticulously tracking their paths using the faint ping of their radio signals. By the 1980s, they noticed something deeply puzzling. Both Pioneers were not quite where they were supposed to be, An incredibly tiny, unaccounted-for force seemed to be acting on them, a constant sunward tug that was slowing their outward journey by a minuscule amount. The discrepancy was almost laughably small, equivalent to a 10 billionth of the gravity you feel standing on Earth's surface. But over billions of miles, that microscopic deceleration added up, putting the probes hundreds of thousands of miles off their predicted course. This was the Pioneer anomaly, a ghost in the machine of celestial mechanics. For years, it haunted the edges of physics. Could it be evidence of some new, unknown force in the cosmos? Was it a hint that our understanding of gravity itself, as described by Einstein, was incomplete at the very edges of the solar system? The anomaly became a siren song for theorists, inspiring proposals about dark matter, modifications to gravity, and other exotic ideas. But the most likely answer, as is often the case in good detective stories, lay not in rewriting the laws of physics, but in a painstaking examination of the crime scene. The spacecraft themselves were the prime suspects. Pioneer was powered by radioactive plutonium pellets, whose decay generated both electricity and, crucially, waste heat. That heat had to be radiated away into space to keep the spacecraft's instruments functioning. Scientists realized the spacecraft's design was not perfectly symmetrical. The heat radiating from the electronic boxes and the power system did not push outward evenly in all directions. More thermal photons were emitted from the back of the spacecraft's dish antenna, which faced toward the sun, than from the front. This created a tiny but constant recoil force, like the faintest of breaths pushing back on the probe. It was the spacecraft's own warmth gently breaking its journey into the void. After years of reconstructing Pioneer's complex thermal blueprint and sifting through decades of old engineering data, a team published a comprehensive analysis in 2012. They concluded this anisotropic or lopsided thermal radiation was almost certainly the culprit. The Pioneer anomaly was not a crack in the foundation of physics, but a masterclass in measurement. It showed that when you track an object with exquisite precision across the solar system, you must account for absolutely everything, even the faint pressure of its own body heat whispering against the infinite dark. The Pioneer probes taught us to listen to the faintest whispers of data, and what we have heard since has fundamentally rewritten the cosmic census. For most of human history, we knew of only 8 planets, all orbiting our single familiar star. The very idea of planets circling other suns was a speculative dream. That all changed in a single generation, leading to one of the most staggering statistical conclusions in modern science. There are likely more planets in our galaxy than there are stars. Let that sink in. The Milky Way is home to somewhere between 100 billion and 400 billion stars. If planets outnumber them, we are talking about a galaxy teeming with hundreds of billions, perhaps even a trillion worlds. This revelation is the direct result of missions like NASA's Kepler Space Telescope, a planet-hunting observatory that stared at a single patch of sky for nearly a decade. Its method was ingenious and simple. It watched for the tiny, periodic dimming of a star's light caused by a planet passing or transiting in front of it. Think of it as detecting a gnat flying across a searchlight from thousands of miles away. The data Kepler sent back was nothing short of revolutionary. It revealed that planets are not the rare exception, they are the cosmic rule. The telescope found that most stars host at least one planet, and many are home to complex multi-planet systems, miniature solar systems with their own intricate gravitational dances. The galaxy is filled with a bewildering variety of these worlds, from gas giants larger than Jupiter orbiting scorchingly close to their stars, to rocky planets in the temperate Goldilocks zone where liquid water could exist. The sheer abundance of rocky, Earth-sized planets was perhaps the most profound takeaway, suggesting the basic ingredients for a world like ours are common construction materials in the universe. This transforms our perspective completely. We no longer look at a star as a solitary beacon. Instead, we see it as the gravitational anchor for a family of worlds, each with its own unique history and potential. The night sky is no longer a scattering of lonely points of light, but a map dotted with billions of unseen solar systems. It means that the cosmic real estate for potential life is vaster than we ever dared hope. While finding a planet with the right conditions is one thing, and finding evidence of life upon it is another challenge entirely. The first and most critical requirement has been met. There is no shortage of addresses in the galactic neighborhood. The universe, it seems, is in the business of making planets, and it is extraordinarily good at its job. Among this galactic bounty of worlds, the ice giants Neptune and Uranus hold a secret of almost unimaginable extravagance. Deep within their frigid blue-green atmospheres, scientists believe it rains diamonds. This is not poetic license, but a serious hypothesis born from our understanding of chemistry under crushing extremes. These distant planets are composed largely of hydrogen, helium, and compounds like water, ammonia, and methane. It is that last ingredient, methane, which is the key. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. In the upper atmospheres of these worlds, powerful lightning storms can rip those molecules apart, freeing the carbon. Now, imagine that free carbon being pulled down by the immense gravity, sinking into layers of the atmosphere where the pressure is millions of times greater than Earth's sea level and temperatures soar to thousands of degrees. Under those hellish conditions, something remarkable happens. The carbon atoms are squeezed together with such incredible force that they crystallize, forming the same molecular structure as the diamonds in an engagement ring. These diamond particles, perhaps no larger than pebbles or even as big as boulders, would then continue their long descent through slushy layers of water and ammonia, falling like glittering, hard hail for thousands of miles toward the planet's rocky cores. We have never directly observed this phenomenon, of course, but laboratory experiments on Earth have successfully recreated the necessary conditions, using powerful lasers to shock hydrocarbon materials and produce tiny nanodiamonds. The physics checks out. This hypothesized diamond rain illustrates a fundamental truth about the cosmos. The conditions on other worlds are not merely variations of our own. They can be so alien, so extreme, that they transform familiar substances into forms of almost mythical wonder. On Earth, diamonds are rare treasures formed deep in the mantle over billions of years. On Neptune and Uranus, they may be as common as raindrops, a routine part of the atmospheric weather cycle in a realm of perpetual, beautiful violence. The diamond rains of distant ice giants reveal a universe of alien majesty, but the most transformative discovery in space may be the one we make about ourselves. Floating high above the atmosphere, gazing back at the shimmering arc of our planet, astronauts experience a profound psychological shift so consistent it has earned a name, the overview effect. This is not a simple feeling of awe, it is a deep cognitive recalibration of one's place in the universe. The view from orbit strips away the imagined divisions that define our lives on the surface. From that vantage point, there are no political borders etched across the continents, no flags, no visible evidence of the conflicts that consume us. What remains is a single, breathtakingly beautiful and heartbreakingly fragile oasis of life, suspended in an endless black vacuum. Astronaut Edgar Mitchell, who walked on the moon during Apollo 14, described it as a visceral, overwhelming sense of universal connectedness. He said, "You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to do something about it." From out there on the moon, international politics look so petty. You want to grab a politician by the scruff of the neck and drag him 250,000 miles out and say, "Look at that, you son of a bitch." His words capture the raw, emotional jolt of the experience, a sudden understanding that the arbitrary lines we draw are invisible from the only perspective that truly matters. More recently, International Space Station astronaut Ron Garan spoke of seeing the world as a fragile oasis that we must work together to protect. He described a sobering contradiction between the stunning beauty he witnessed and the widespread suffering and environmental degradation he knew existed below. For these explorers, space travel becomes an unexpected journey inward, forcing a confrontation with the unity of humanity and the planet that sustains us all. This cognitive shift is a unique and wonderful side effect of leaving our world, a side effect with potentially revolutionary implications. If the overview effect could be somehow imparted to every person on Earth, how might it change our approach to global crises like climate change, poverty, or conflict? It argues that the greatest value of space exploration may not be the minerals we mine or the planets we map, but the new perspective we bring back home, a reminder that we are all crew members on the same delicate spacecraft sailing through the cosmic dark. That profound shift in perspective was made possible by robotic eyes that first mapped the way. While Apollo astronauts were making history with their footprints, another, quieter explorer was already rolling across the lunar dust. In November of 1970, the Soviet Union achieved a staggering robotic first, landing a remote-controlled rover on the moon named Lunokhod-1. It was a masterpiece of Cold War engineering, a vehicle that looked like a giant metallic bathtub perched on 8 spindly wheels. Under its hinged lid were solar panels to power its systems during the long lunar day, and inside was a suite of cameras, an X-ray spectrometer, and a laser reflector. For nearly 10 months, controllers in the Soviet Union guided this one-ton machine across the Sea of Rains. They navigated by watching its stereo camera feeds on television screens, steering it carefully around craters and boulders. Lunokhod-1 traveled over 6 miles, sent back thousands of photographs, and performed hundreds of soil analyses, becoming the first remote geologist on another world. Its mission was a monumental success, proving that complex robotic exploration was not only possible but incredibly valuable. Then it fell silent. As the lunar night descended for the final time, its radioactive heat source depleted, the rover went dormant. For decades, its exact final resting place was lost, a forgotten relic of a secretive space program. That is, until 2010, when scientists analyzing images from NASA, a lunar reconnaissance orbiter, spotted it. There, clear as day, were the tracks and the rover itself, sitting silently where it had stopped 40 years prior. The real surprise came when researchers aimed a powerful laser at Lunokhod's reflector from Earth. To their amazement, it pinged back a signal, reflecting light with a clarity that was, at times, even better than the reflectors left by the Apollo astronauts. This forgotten Soviet machine was suddenly a vital piece of modern science, helping to measure the moon's orbit and gravitational field with exquisite precision. The story of Lunokhod-1 is a tale of two kinds of legacy. It is a testament to brilliant, forgotten engineering that pushed the boundaries of what machines could do in space, often overshadowed by the dramatic human stories of Apollo. And it is a reminder that in exploration, nothing is ever truly lost. A tool built for one purpose can, decades later, awaken to serve science in ways its creators never dreamed, its silent form on the dusty plains still speaking to us across the void. Lunokhod's silent reflector still sends a faint signal home, but from the deepest reaches of the cosmos, the universe broadcasts screams. These are not whispers or echoes, but sudden, violent shrieks of pure energy known as fast radio bursts. In just a few thousandths of a second, one of these bursts can release more energy than our sun emits over 80 years. A power equivalent to 500 million suns concentrated into a flash shorter than a camera's blink. They were first discovered by accident in 2007, when an astronomer named Duncan Lorimer was sifting through old data from a radio telescope in Australia, searching for distant pulsars. He found something far stranger, a single, brilliant spike of radio noise recorded 6 years earlier, a spike that did not fit any known pattern. For years, it was considered a possible fluke, a one-off glitch in the data. Then more were found. Today, we know these events are happening constantly across the sky, with hundreds detected and likely thousands occurring every single day. The challenge is catching them because they are here and gone before you can even blink, leaving behind only a ghostly fingerprint in a telescope's memory. So what could possibly create such a staggering, fleeting explosion? The leading suspects are some of the most extreme objects in existence. Magnetars, for instance, are a type of neutron star with a magnetic field so powerful it could erase a credit card from halfway across the solar system. A starquake on such an object, a sudden snapping of its rigid crust under unimaginable magnetic stress, could theoretically unleash the focused energy of a fast radio burst. Yet not every burst fits this mold. Some have been observed to repeat, sending out multiple signals from the same patch of sky, which rules out any cataclysmic one-time event like a star exploding or two black holes colliding. This repetition deepens the mystery, pointing to a source that can survive its own apocalyptic outburst and fire again. The hunt for their origins is now a global scientific race, using networks of telescopes that can swivel at a moment's notice to triangulate the location of a burst as it happens. Each new detection is a piece of a cosmic puzzle, a clue to physics operating at energies we cannot hope to recreate on Earth. They are reminders that the universe is not a quiet, static place, but a dynamic arena where titanic, invisible forces can announce themselves with a sudden, deafening roar across billions of light years, challenging us to decipher their message. While fast radio bursts scream across cosmic distances, on one world in our own solar system, time itself moves to a bizarre and disorienting rhythm. A single day on Venus is longer than its entire year. This is not a trick of language, but a literal truth born from the planet's peculiar spin. Venus takes 243 Earth days to complete one full rotation on its axis, what we would call a day. Yet it only needs 225 Earth days to complete one full journey around the Sun, its year. If you could stand on that scorching surface, you would experience a sunrise in the west, watch the sun crawl agonizingly slowly across a hazy, orange sky, and then see it set in the east 243 days later. And in that time, the sun would have completed its own full cycle in the sky, meaning a Venusian year would have passed before its day was even over. This leads to a truly surreal calendar where the sun rises only twice during each orbital period. What could cause a planet to spin so slowly and in the wrong direction? A motion astronomers call retrograde rotation. The leading theory points to a violent, chaotic infancy. Early in the solar system's history, a massive protoplanet, perhaps as large as Mars, may have slammed into a young Venus. This colossal impact would have delivered an incredible amount of angular momentum, essentially hitting the planetary brakes and tipping it over, causing it to spin backwards. Over billions of years, the gravitational tug of the Sun on Venus's thick atmosphere, combined with tidal forces, may have further slowed that spin to its current lethargic crawl. This bizarre rotation has profound consequences for the planet's nightmarish environment. The incredibly long days and nights create extreme temperature differences that, coupled with the planet's thick carbon dioxide atmosphere, contribute to a runaway greenhouse effect. The surface bakes at nearly 900 degrees Fahrenheit, hot enough to melt lead, with pressures 92 times greater than Earth's sea level. The slow spin also means that Venus lacks a protective global magnetic field like Earth's, as its core may not churn vigorously enough to generate one, leaving the atmosphere exposed to the full fury of the solar wind. This single, weird fact about its day and year is the key that unlocks the story of a world that took a very different path than our own, a planet where time itself stretches into a hellish, sun-baked eternity. Venus spins in a slow, backward nightmare, but the early space age was haunted by an even darker legend. In the feverish secrecy of the Cold War, a terrifying rumor took root: the story of the lost cosmonauts. The tale claimed that the Soviet Union, desperate to beat America into space, had launched men and women before Yuri Gagarin's triumphant orbit in April of 1961, and that those pioneers had perished in silence, their deaths covered up by a state obsessed with propaganda. The evidence for believers seemed chillingly concrete. In the late 1950s and early 60s, amateur radio operators across Europe claimed to have intercepted desperate, crackling transmissions from orbit. The most famous came from the Italian brothers Achille and Giovanni Giudica Cordiglia, who recorded what sounded like a failing heartbeat and labored breathing from a spacecraft, followed by a faint voice in Russian pleading for help. They also claimed to have recorded a female cosmonaut, later dubbed Ludmilla, whose craft was allegedly spiraling out of control. These tapes, combined with the Soviet Union's notorious culture of secrecy, created a perfect storm for conspiracy. When a mission failed, the state simply erased it from history, refusing to acknowledge anything but success. This practice was confirmed with later disasters like the Soyuz 1 and Soyuz 11 tragedies, which were initially hidden before the truth emerged. That pattern of concealment made the idea of earlier, hidden casualties feel terrifyingly plausible. So, where does the historical truth lie? Declassified documents and meticulous research by historians after the Soviet Union's collapse have painted a clearer, though still shadowy, picture. There were absolutely fatal accidents on the ground. In 1960, a horrific explosion at the Baikonur Cosmodrome killed an estimated 126 people, including the brilliant Chief Marshal of Artillery, Mitrov von Nedelin, a catastrophe hidden for decades. There were also unmanned test flights that exploded or veered off course, which state radio would sometimes report as scientific satellites, further muddying the waters. As for the famous intercepted transmissions, experts have largely debunked them. The technology available to the amateur listeners was primitive, and the signals they claimed to capture would have been far too weak to receive on Earth with their equipment. The emotional Russian pleas were likely fabricated or misinterpreted from other broadcasts. Most conclusively, there is no paper trail, no internal memo, no witness testimony from within the massive Soviet space program that supports a manned launch before Gagarin. The consensus among historians is stark. While the Soviets brutally covered up many failures and ground fatalities, there is no credible evidence they ever placed a human in a spacecraft before Yuri Gagarin. The lost cosmonauts endure not as history, but as a powerful psychological artifact of the Cold War. They are the ghosts born from the marriage of absolute secrecy and human fear, a legend that reminds us that in the darkness of the unknown, we sometimes see the monsters we expect to find. Our sun's influence reaches far beyond the last planet, extending into a realm of almost pure theory and profound darkness. The boundary of our solar system is not marked by Pluto or even the scattered disk of icy objects beyond it, but by a colossal, hypothetical shell of frozen debris known as the Oort cloud. Imagine the solar system not as a flat disk, but as a vast spherical bubble. The planets orbit in a relatively thin plane near the center, but this bubble, this cloud, envelops everything in a shell of icy remnants from the system's violent birth. These are not compact worlds, but trillions upon trillions of frozen lumps, each a potential comet nucleus, each a pristine relic from over 4.6 billion years ago. They are so distant and so dark they have never been directly observed, their existence inferred solely from the behavior of the rare comets that visit our skies. This is where the sun's gentle gravitational whisper finally fades into the silence of interstellar space. The scale is almost impossible to comprehend. While Pluto orbits at an average distance of about 3.7 billion miles from the Sun, the inner edge of the Oort cloud is thought to begin roughly 2,000 times farther out. Its outer boundary may stretch nearly a light year into the void, a quarter of the way to our nearest stellar neighbor, Proxima Centauri, At such distances, a single orbit around the Sun could take millions, even tens of millions of years. These frozen sentinels are the solar system's ultimate time capsules, orbiting in a deep freeze so profound that their chemistry has been unchanged since the dawn of our planetary family. Their immense distance also makes them incredibly fragile. The gentle gravitational nudge from a passing star or the tidal pull of the Milky Way itself can be enough to dislodge one of these icy bodies from its lazy orbit. When that happens, the object begins a fall of epic proportions, a plunge inward that can last thousands of years. Accelerating as it goes, it eventually screams into the inner solar system as a spectacular long-period comet, its frozen volatiles boiling off in the sun's heat to form a brilliant tail that may stretch across the heavens. The Oort cloud is the ultimate source of these celestial wanderers, a distant reservoir that occasionally, and without warning, hurls a piece of our primordial past directly at us. It defines the true extent of our celestial home, a ghostly, spherical frontier where the sun's dominion ends and the great galactic ocean begins. Newton's third law is an unforgiving supervisor on a spacewalk. Every action truly does have an equal and opposite reaction, a principle that can turn a simple task into a life-threatening emergency. If an astronaut pushing off from the spacecraft applies a little too much force at a slight angle, they can inadvertently send themselves into a slow, uncontrolled spin. Tumbling head over heels while untethered, with the vast, starry void whirling around you, is more than just disorienting. It can induce severe nausea, make it impossible to focus on your work, and critically, prevent you from reaching a handhold to stop yourself. In the early days, the only solution was for a fellow astronaut to carefully float over, grab the spinning crewmate, and use their own body as a counterweight to halt the rotation. It was a risky, clumsy maneuver. Today, they have a far more elegant and independent tool, one that looks like it belongs in a science fiction arsenal, the pistol grip tool. This is not the power drill used to bolt panels onto the International Space Station, though it shares the same basic shape. This specific device is a handheld, gas-powered jetpack. It works on the simplest possible application of Newton's law. The astronaut simply aims the tool in the direction opposite their spin and pulls the trigger. A controlled burst of cold nitrogen gas shoots out, providing a precise thrust that pushes the astronaut's body in the opposite direction, canceling out the unwanted rotation. It is the ultimate self-rescue device, turning a terrifying tumble into a manageable correction with a gentle squeeze of the finger. The genius of this tool lies in its beautiful simplicity. It requires no complex electronics or software, just pure physics made manifest in a handheld form. It empowers an astronaut to be their own anchor, to correct a dangerous mistake with calm precision. This small, clever gadget embodies a central truth of space exploration. Surviving the final frontier is not just about courage and advanced rockets. It is about anticipating every possible way the universe can throw you off balance and having a smart, reliable way to push back. That ghostly frontier of the Oort cloud occasionally sends messengers rocketing toward us, and some of those messengers carry secrets from our closest planetary neighbor. In 2005, a meteorite hunter working in the high desert of Tibet made an extraordinary find. Nestled among the stones was a dark, weathered rock, roughly the size of a clenched fist. Its shape was unusual, appearing to naturally resemble a human figure seated in a classic pose of meditation. To some who saw it, the resemblance was uncanny, a serene, stone Buddha that had fallen from the heavens. This fragment of space rock was quickly nicknamed the Space Buddha meteorite. The cultural wonder of its shape is a beautiful coincidence, a fresh example of our brain's tendency to find familiar forms in the random artistry of nature. Yet the true wonder of this rock lies not in its silhouette, but in its origin story, a story written in the chemistry of its glassy heart. Scientific analysis revealed this was no ordinary asteroid fragment. It was a shergotite, a type of igneous rock blasted from the surface of Mars. But how can we possibly know a rock found on Earth came specifically from the red planet? The proof is locked inside tiny bubbles of ancient gas. When scientists crush a minuscule sample of a Martian meteorite in a vacuum chamber, they can analyze the gases that are released. The fingerprints are unmistakable. The ratios of different isotopes of noble gases like argon, xenon, and neon, and the specific mix of nitrogen and carbon dioxide match perfectly with the atmospheric data sent back by the Viking landers in the 1970s. It is a perfect cosmic match, like finding a bottle with a message inside and then confirming the handwriting belongs to a specific person you know. The journey of such a rock is a saga of cosmic violence. An asteroid or comet must slam into Mars with such colossal force that it excavates material and propels it upward at a speed exceeding Mars's escape velocity, over 3,000 miles per hour. These ejected rocks then enter orbits around the Sun, where they drift for millions of years, a silent fleet of interplanetary debris. Through gravitational nudges and chance encounters, a tiny fraction of these travelers eventually cross paths with Earth, streaking through our atmosphere in a fiery descent. The Space Buddha survived that inferno, its outer layer melting into a dark, glassy crust called a fusion crust, while its interior remained a pristine sample of Martian geology. To hold such a meteorite is to hold a piece of another world that traveled hundreds of millions of miles to reach us. It is a tangible bridge across the void, a scientific specimen that validates our understanding of planetary atmospheres, and a cultural artifact that sparks our imagination. It reminds us that the planets are not isolated islands, but connected members of a dynamic solar system, occasionally swapping pieces of themselves in the most dramatic way possible. But where exactly does the atmosphere end and space begin? The answer is surprisingly arbitrary, and it is marked by a line in the sky named for a brilliant engineer. The Kármán line, set at 100 kilometers or 62 miles above sea level, is the internationally accepted boundary of outer space. Its namesake, Theodor von Kármán, was a pioneering aerospace scientist who calculated the altitude where the very nature of flight fundamentally changes. His reasoning was elegant and practical. Below this line, an aircraft can stay aloft using traditional aerodynamics, generating lift by pushing against the molecules of air with its wings. But as you climb higher, the atmosphere becomes exponentially thinner. At the Kármán line, the air is so rarefied that a vehicle would have to travel at orbital velocity, roughly 17,500 miles per hour, to generate enough aerodynamic lift to keep from falling back to Earth. At that speed, you are no longer flying, you are orbiting. It is the altitude where the physics of aviation gives way completely to the physics of astronautics. Yet this line is not a physical wall, but a legal and conceptual one. The debate around it is fierce. Some argue it should be lower, at 80 kilometers, where certain atmospheric phenomena like noctilucent clouds occur. Others point out that the atmosphere's faint outer tendrils extend for thousands of miles, meaning there is no true, clean edge. But the Kármán line's importance is immense precisely because we needed to draw a line somewhere. It is the altitude that defines who is an astronaut. It determines world records, dictates which flights require spaceflight licenses, and underpins international treaties that govern where a nation's airspace ends and the global commons of space begins. Today, as private companies like Blue Origin and Virgin Galactic sell tickets for suborbital joyrides, this invisible boundary has become a multi-million-dollar finish line. Crossing it, even for just a few minutes of weightlessness, is the ultimate bragging right and a legal milestone. The Kármán line stands as a testament to human ingenuity, a line we drew not because nature provided it, but because our ambition demanded a place to start. The Kármán line defines where our atmosphere surrenders to space, but one of our most persistent cosmic myths is about a place that is not dark at all. We call it the dark side of the moon, a name that conjures images of a hemisphere locked in eternal cold shadow. This is a complete misnomer. The far side of the moon receives just as much sunlight as the side that smiles down on us every night. It experiences 2 week-long days and equally long nights, a cycle perfectly in sync with our own familiar lunar phases. The reason we never see that half from Earth is a beautiful accident of celestial mechanics called tidal locking. Billions of years ago, the moon rotated at a different speed, but Earth's powerful gravity, acting on the slightly uneven mass of the young moon, acted like a gentle but relentless brake. Over eons, this gravitational tug slowed the moon's spin until its rotation perfectly matched its orbit around our planet. Now, it takes the moon the same amount of time to spin once on its axis as it does to complete one trip around Earth. The result is that one face is permanently turned toward us, like a partner in a slow, eternal dance. The other side remained a total mystery until the space age, a blank canvas upon which we could paint any fantasy. For centuries, writers and theorists speculated wildly about what might be hidden there, imagining lush jungles, alien bases, or vast frozen oceans. The truth was finally revealed in 1959 by the Soviet Luna 3 probe, which swung around the moon and snapped the first grainy, ghostly photographs. The images were a shock. The far side looked utterly alien, a battered, pockmarked landscape completely different from the familiar face we knew. It was dominated by rugged highlands scarred with countless craters and almost entirely lacking the large, smooth, dark plains we call Maria or seas that define the moon's Earth-facing side. Scientists now understand this asymmetry is due to the far side's crust being significantly thicker. When giant asteroids struck the moon in its youth, molten lava from the interior could more easily flood the impact basins on the thinner crust near side, creating those vast, flat seas of solidified basalt. On the far side, the thicker crust acted like a stronger shield, preventing most of that lava from welling up, leaving the ancient cratered highlands exposed. So the far side is not dark, but it is profoundly different, a more primitive and rugged record of the solar system's violent early history, forever hidden from our direct view, yet now intimately known by our robotic ambassadors. The Apollo missions gave us more than moon rocks and inspiration. They gave us the invisible technology woven into the fabric of our daily lives. This is the legacy of spin-offs, the countless innovations born from solving the extreme problems of spaceflight that later found a home on Earth. While stories of Tang and Velcro are common, the real impacts are far more profound and often life-saving. Consider the modern CT scanner, a device that revolutionized medical diagnostics. Its core technology came directly from NASA, a need to enhance fuzzy, low-contrast images of the moon. Engineers developed a process called digital image processing to sharpen those pictures, a technique that was later adapted to create the detailed, cross-sectional views of the human body we rely on today. That scan that helps diagnose a tumor or a fracture has a direct lineage to the first clear photographs of the lunar surface. Then there is the cushioning in your mattress or your favorite chair. Memory foam was invented by NASA-funded researchers in the 1960s to improve seat cushioning and crash protection for astronauts. This temperature-sensitive material, which molds to the body and then slowly returns to its original shape, was a solution for the intense G-forces of launch and re-entry. It was released to the public in the early 1980s and has since become a standard for comfort and medical support, helping to prevent bed sores in hospitals and providing relief in millions of homes. Even the water you drink may be cleaner because of space. The rigorous filtration and purification systems developed for the Space Shuttle and the International Space Station, which must recycle every drop with absolute reliability, have led to advanced municipal water treatment systems and portable filters used in disaster zones and remote communities around the world. And next time you use a wireless headset or earbuds, Thank the need for astronauts to move freely without cumbersome cords during spacewalks. The technology for reliable, hands-free communication in a bulky suit drove the development of the lightweight, wireless systems we now take for granted. These are not happy accidents, they are the direct result of a simple truth. When you are forced to solve a problem where failure is not an option, where every gram and every watt counts, and where human lives depend on absolute precision, you cannot rely on existing solutions. You must invent new ones. The investment in reaching for the stars has always yielded a rich harvest here on the ground, proving that the quest to understand the cosmos is also, fundamentally, a quest to improve life on our own pale blue dot. The technology that returns to Earth from our voyages is tangible, but the most transformative ideas often remain, for now, trapped in the elegant prison of mathematics. At the very edge of theoretical physics lies a concept so wonderful it feels like a gift from science fiction, a genuine proposal for a warp drive. In 1994, Mexican physicist Miguel Alcubierre published a paper that sent shockwaves through the scientific community. He asked a simple, profound question: could you travel faster than light without actually breaking Einstein's sacred rule that nothing can move through local space faster than light? His answer, sketched out in the complex language of general relativity, was a tentative yes. The Alcubierre drive would not propel a ship through space. Instead, it would manipulate the fabric of spacetime itself. Imagine a surfer riding a wave. The surfer does not paddle faster than the water. The wave carries them forward. Alcubierre's design creates a similar warp bubble around a spacecraft. This bubble would contract the spacetime directly in front of the ship, pulling the destination closer, while simultaneously expanding the spacetime behind it, pushing the point of origin farther away. Inside this bubble, the ship sits in a flat, stable pocket of spacetime. It experiences no acceleration forces, no time dilation, and crucially, it never moves through the space inside the bubble faster than light. The bubble itself, however, containing the distorted spacetime, could theoretically propel the ship to its destination at speeds many times faster than light. It is a breathtakingly clever loophole in the laws of physics, but this wonderful idea comes with equally monumental problems, barriers so immense they currently make the drive impossible. The first is energy. Early calculations suggested creating such a warp bubble would require an amount of negative energy equivalent to converting the entire mass of Jupiter into pure energy, a scale beyond any technology we can conceive. Negative energy is a speculative concept where a region of space has less energy than empty vacuum, a phenomenon hinted at in certain quantum effects but never observed at the macroscopic scale needed for a warp bubble. The second problem is control. How would you create the bubble? How would you steer it? And most frighteningly, how would you stop it? Some calculations suggest particles of radiation could build up at the edges of the bubble, and upon deceleration, they would be released in a catastrophic burst of energy, obliterating anything at the destination. For now, the Alcubierre drive remains a glorious thought experiment, a set of equations on a page that tells us the universe's rulebook might, just might, contain a chapter on faster-than-light travel we have not yet learned to read. Its value is not as a blueprint for tomorrow's engine, but as an inspiration. It proves that within the rigid framework of known physics, there is still room for wonder, for daring to ask if the greatest limitations are not in the laws of nature, but in the boundaries of our own imagination. It is a beacon for future generations of physicists, a challenge written in the language of space-time, waiting for someone to find the key. From the elegant mathematics of warp drives to the lonely sacrifice of a stray dog, our journey through these 30 wonders reveals a profound truth. Space exploration is not a single story of cold technology or distant stars. It is a tapestry woven from equal parts human curiosity and tragic sacrifice, brilliant engineering and humbling cosmic mystery. We have seen how the universe challenges our bodies, stretches our spines, and rewrites even our tears. We have followed robotic pioneers through radiation belts and diamond storms, listened for whispers in the cosmic static, and learned that our greatest discoveries often begin with a single, vulnerable step into the unknown. These stories dismantle the idea of space as a silent, empty void. Instead, they paint a portrait of a dynamic and astonishing arena, filled with the lingering scent of dead stars, the silent rain of precious stones, and the echoes of explosions that outshine galaxies. It is a realm of endless challenge, yes, but also of infinite potential. Every weird fact is a doorway to a deeper wonder, every answered question births 10 more, and every risk taken expands the horizon of what is possible for our species. This is the legacy we are building, one of relentless curiosity tempered by responsibility, of reaching for the stars while never forgetting the fragile blue dot we call home. So, what fact resonated most with you? Was it the overview effect that changes an astronaut's soul, the haunting mystery of the wow signal, or the simple, profound truth that we are made of stardust? Share your favorite cosmic wonder in the comments below. If this journey through the stars sparked your imagination, subscribe for more explorations into the universe's greatest mysteries. And tonight, when you step outside, take a moment to look up. Remember that in that vast, glittering darkness, there are worlds where it rains diamonds, robots that still call to us after decades of silence, and wonders beyond our wildest dreams, all waiting to be discovered. Keep looking up.